So while I'm transitioning over to our slides, I will mention that tonight we're going to cover 3 sections in chapter 4, and then that will leave next Monday night. We will cover the remaining 2 sections and the final exam review. And then the week after, well, let me actually just double check. And then the week after that, we'll have our final exam review. And then the final exam itself will be on the 11th of November, I believe. So I'm going to just pull up the schedule real quick and double check that to remind you all. Give me half a second. All right, so tonight, tonight we're covering sections 4, 1, 2, and 3. Next Monday, we'll do sections 4 and 5. And then the following Monday, December the 4th, we'll do our final exam review. That will give you all time to have worked the last of chapter 4, have any questions if you may. We'll do that final exam review on December 4th, and then the final exam itself will be on Monday, December 11th. Okay? Any questions about what the expectation is for the remainder of the semester? Okay. All right. So what we're going to cover tonight then is we're going to start looking at integration, right? So why is integration important? Integration is actually one of 2 main branches of calculus, with differentiation being the other, right? And so integration is the process of adding slices to find the whole. So if you think about it in terms of if we wanted to understand the area under a curve, right? So if we have something that looks like this and we have some sort of curve, right? And we want to understand the area under the curve. Well, we don't really have a way to measure that, but if we break it into small little pieces and add all that up, we can get a better idea of a more accurate calculation on that, right? So our integration techniques we'll be able to use to find areas, volumes, central points, and lots of other useful things, okay? So in this first section here on anti-differentiation, that starts on page 386 of your textbook. And so the thing to point out here is we just finished chapters 1 through 3, where we covered differential calculus. Now we're going to shift gears a little bit and cover what's called integral calculus, okay? And so the first theorem that we have here is that the antiderivative of a function is the set of functions where we have capital F of x plus c such that the derivative of this set of functions plus some c, which is some constant, is equal to the function itself. So what I like to say here is that anti-differentiation is really very similar to reverse engineering the derivative, right? So if you think about it, is now you're given the derivative and you want to come out and determine what the actual function was, okay? And so anti-differentiation is often called integration, okay? And so an example might be if you were asked to indicate the antiderivative of x squared, right? So what is the antiderivative of this? So basically, the antiderivative then is going to be x cubed over 3 plus some constant c. And so how do we get to that? That's what we're going to learn over the course of this evening and into next class period. But essentially, if I take the derivative of this, I actually get back to that x squared, right? Because the derivative of x cubed over 3, right, is just, the derivative is 3x squared over 3 plus that constant, and we know that the derivative of a constant is 0. So you can see here that yes, in fact, if we were to take the derivative of this plus this constant here, right, that derivative is going to be x squared. And so my original function would be this x cubed over 3 plus c, and my derivative of that would be x squared. So when I'm doing the antiderivative, I'm given the derivative and asked to tell you the formula. Okay, question. Okay, so the second theorem that we have here, okay, is so we have just a set of rules, so to speak, right? So we can say if it's the constant rule, that's that constant k, right? Then the antiderivative is going to be kx plus some c. So the one thing I will tell you, when we're talking in general form, you must always include that plus c out there, or you will lose a point or two if it's on an exam, if you don't have that constant out there. Now, if we're actually, and you'll see in future sections, if we're looking at this from 0 to 2 or something like that for actual interval, then that c does not belong there, but we'll work through examples of all of them. Right. Okay, so we have a constant rule, we have a power rule. So this tells me that example that I had a while ago, right? We had x squared. So really, if I had asked you what's the integral, that's this little crazy looking little f sign. The integral of x squared dx, remember we started putting this dx, right? That's the rate of change of x. We started doing that in the last class period or two as well. So if I want to know what's the antiderivative of this, that is, we could say, okay, my n in this case is 2. So then it's going to be this right here. So it's going to be 1 over 2 plus 1 x over 2 plus 1 plus c. And that simplifies down to this x cubed over 3 plus c. Okay, so that was the example we used previously. All right, so what if I'm looking at natural logs? So that is, if I have 1 over x, that is really the same as the ln of the absolute value of x plus that constant. Or if I'm limiting x to being greater than 0, then I can say that that's just simply 1 over x is equal to ln of x, and I don't have to have the absolute value on that x because I've already restricted it to being positive. Okay? Or greater than 0. Question. So then if we're looking at our exponential rule, this is e raised to some ax, then that's really just 1 over a times e to the ax plus that constant c. And our a cannot equal 0 because it will make our function there undefined. Okay, question. Okay. So we also have some properties of antiderivatives. So basically this is saying if I have some integral and I have some constant times a function, we can bring the constant to the outside and then just integrate with the function itself. Okay. And the other one is very much like the product rule. If I have one function plus or minus another function, that could just be integrate each of them individually, and that works as well. Okay? Questions? Okay? So this first problem we have here is 4dx. So that's a constant. So based on the constant rule, that would be 4x plus c. We can actually check our work here. Okay, so we check our work and we know that the derivative d dx of 4x plus c, right? That's what we came up with. What is the derivative of that? Well, that derivative is equal to 4. That is what we were looking for up here. So check, that is correct. Okay, questions? Okay. Let's look at this next one. So it's just a power rule where our n is equal to 7. So this is going to equal x 7 plus 1 divided by 7 plus 1. Let's not forget that c constant out there. And we get that is x to the 8th over 8 plus c. Now let's check our work. If I take the derivative of d dx of x over 8, 8 plus c, then I get, this comes back to x to the 7th, which is what we were looking for here, and that checks out. Okay, questions?
Professor, how did you get x 8 over, how did you get x over 7?
I'm so x
confused.
raised to the 7?
Yeah, x raised to 7.
When I take the derivative, d dx of x to the 8 over 8 plus the derivative of that constant, right? So the derivative of 8x over 8, that becomes the derivative here, right, is 8. So it becomes 8x to the 7 because we have to minus 1 off of that over 8. And then the 8's cancel and we're left with x to the 7.
Okay, thank you.
Of course. And then the derivative of a constant is 0. Okay. Questions? All right. And so for this last one here, we have that equals x to the 1/3 plus 1 over 1/3 plus 1 plus c. So we end up, I'm going to have to erase this work. Sorry. We have x to the 4/3 over 4/3. So this, let's not forget the c. So that becomes, so if I had x raised to the 4/3 divided by 4/3, that's the same as multiplying by the reciprocal, and then we still have that plus c out there. So this actually becomes, in simple forms, 3x to the 4/3 over 4 plus c. Okay, question? All right, so now let's look at a little bit more complex. So again, this one would be like saying the integral of 3t squared minus the integral, but we have to put the dt on here, sorry. dt minus the integral of 4t dt plus the integral of 7 dt, right? So we can break this down in all of these. So what derivative do I need that would give me this 3t, right? So we could have this would be like, so we have the 3t, we have this 2 2 plus 1. And then over here we have this 2 plus 1, right? And so that gives me, this becomes 3 in the denominator, so it leaves me just with t cubed. Okay, does everybody see how that one piece, let me shift this down just a little bit, how that one piece there becomes t cubed, okay? Minus, well, we can bring this 4 outside, right? If you remember from our constant rule, we could bring that out if we wanted. And so that becomes 4. Now how, like, I need a t squared over 2. If I took the derivative of t squared over 2, that is what? That's 2t squared over 2. I mean, not t squared, t. Those 2's cancel, and that leaves me with a t, so that makes sense, right? So in this case, we would say this simplifies to negative 2t squared. Okay? Questions? So now we have this constant here. Again, we can bring that outside. Okay, so this is plus 7 times, now we have nothing, right? So how do we get to basically just the dt? And that would be if I took the derivative of t, right? So the derivative of t is t. So if I took that, I would end up at just having the dt. And then, of course, let's not, so plus 7t, but let's not forget we always have to add that constant when we're talking about the general terms. Okay, question. Okay. Let's look at this next example then. So for this one, let's go ahead and bring everything up into the numerator. So this would be the integral of 4x to the negative cubed plus 7x to the negative 1 dx. Okay. We can further break that into the integral of 4x to the negative 3 dx plus the integral of 7x to the negative 1 dx. Okay. So when we simplify that, we end up with, for the first one, we end up with negative. So we have the 4, we could bring the 4 out. Let's go ahead and do that. So we can bring the 4 out. We can also bring this 7 out. So this is going to give me 4 times, we have that negative there, right? So it's going to be x negative 3 plus 1, and we have negative 3 plus 1 in the denominator. And so we can simplify this as 4x to the negative 2 over negative 2. We can simplify that one more time to be negative 2x to the negative 2. Okay, now let's work the other piece of the integral. So we have plus, we have that 7 that we've brought out. And what is the antiderivative of x over negative 1? And so in this case, that is the ln of x. And we can either put the absolute value signs on it, or we can say that x is greater than 0. But let's not forget we have to include that plus c out there. Okay. So this we could just bring down here. So that's plus 7 ln of x plus c where x is greater than 0. Okay? And we could have written this one more better. We could have said -2 over x squared plus the 7 ln of x plus c where x is greater than 0. Okay? Question. Okay, so for this next example, similar to the previous problem, let's bring all of that up into the numerator. So we end up with the integral of 5 over x to the 3/4 dx, and that equals the integral of 5x to the -3/4 dx. Okay, so now we can bring this portion out. We don't want it to go on the outside of the equals, but we'll put it in here. And now we can say, okay, so that is equal to 5 times x to the -3/4 plus 1 divided by -3/4 plus 1 plus that constant c out here. Okay? So this would simplify to 5x to the 1/4 over 1/4 plus that constant c, which is equal to 20, because 5 times 4 over 1, right? Because if I'm dividing by 1/4, I can multiply by its reciprocal, is 20. X to the 1/4 plus c. And the last thing we want to do is take that 1/4, let's put it back into root format. So that's 20 fourth root of x plus c. Okay? Question. So this next problem is incorporating our exponents, right? So where we're using the exponent rule. Again, we can bring this 4 to the outside. So we have 4 times e to the 4x. Well, what is our derivative of e to the 4x? It's simply going to be, let's poke over here. So it's 1 over a, right? So it's 1 over 4, because in this case, a is equal to 4, e to the 4x plus that constant c. And so this then would be the 4's cancel with each other, and we get e to the 4x plus c. Okay, question. Okay, let's look at number 34. So the first thing I would say here is let's just multiply this out. Let me get a different shade. Let's just do the math and multiply out first. Okay, so I'll put that here. Multiply first. So this is going to give me the derivative or the integral. If I do this, this becomes e -2x times 3x, not times, plus 3x minus e to the -2x plus 2x. dx. Okay. So when I simplify that, that gives me the integral of e to the x minus e to the 0 dx. So that is the same as the integral of e to the x minus 1 dx. So when I take the antiderivative, that is the antiderivative of e to the x dx minus the integral of 1 dx. So remembering back to our rules, the antiderivative of e to the x is simply just e to the x. And the antiderivative of 1 is x, so that's minus x. And then let's not forget to put our constant out here. Okay? Because if I take the derivative of negative x, I end up with that negative 1 there. Okay? So we could do that check. Question. All right, so let's look at the next kind of problem. So it's a little bit more involved. It has some more steps. So the first thing I'm going to do is I'm going to just bring that x squared up into the numerator. Okay. So if I do that, then that gives me the integral. If I bring up to the top, that is 5x squared x negative squared plus 7x x to the negative square minus 11x negative squared dx. Okay. So simplifying that, we get the integral of 5. It's just 5, right? Because I have x squared minus x squared. So that's 2 minus 2 gives me just 5. Plus, if I have x to the 1 minus 2, right? Because we can just take and add our exponents. So this one is the same as saying x 2 minus 2. So that's x to the 0, which equals 1. Okay. This one is x 1 minus 2, which is x to the negative 1. Okay. So we have that. So plus 7x to the negative 1 minus 11x to the negative 2 dx. Okay. So this gives me 5x as my antiderivative plus 7 ln of the absolute value of x. Again, remember if we put off to the side that x is greater than 0, we don't have to put those absolute values. Minus, this is 11, and then we have x, and we have this negative 2 plus 1 over negative 2 plus 1. And then let's not forget that constant c out there. So now really what we need to do is just simplify our work here. So we have 5x plus 7 ln of x plus 11x to the negative 1. Okay, because we end up here with negative 1. Negative 1 times negative 11 is positive 11. And then up at the numerator, we have x negative 2 plus 1 gives us x to the negative 1. Okay, plus our c out here. And the last thing we can do is rewrite that third term there where it doesn't have a negative exponent. So we have 5x plus 7 ln absolute value of x plus 11 over x plus c. Okay, question. All right, so the last type of example that we have here is we want to find a function, f of x, such that the derivative is equal to x minus 5. And when I evaluate it at f of x equal to 1, my solution is 6. Okay. So how do we do that? We first need to find what f of x is by integrating. Okay, so I'm going to write that out just so you guys have that stepwise. So we find f of x by integrating. Okay, so that is f of x equals the integral of x minus 5, that's our derivative, dx. Okay, so that is the integral x dx minus the integral of 5 dx. So that's on the outside there. And we end up with, this is going to be x squared over 2, right? Because we have that x1 plus 1, right? So x1 plus 1 over 1 plus 1 gives us that x squared over 2, okay? And minus, we have this 5 here, and then the integral of 1 is just x, and we also have to include that constant out there, okay? So this is x squared over 2 minus 5x plus c, okay? Now we want to know where is the condition. So the condition f of 1 equals 6, okay? That allows us to find c. So this allows us to find c, okay? So f evaluated at 1 equals 6. So this gives me evaluated at 1. So we plug that in for our 1. So we have 1 squared over 2 minus 5 times 1 plus c, and this equals 6, okay? Because it tells us that that evaluated at 6 equals 6, okay? So now when we work on this, we have that is 1/2 minus 5 plus c equals 6. So this here is, this is the same as 10 halves, right? So that will give me a negative 9 halves plus c equals 6. And so when we do that, this is the same as saying 12 halves, right? So if I add 9 halves to both sides, that gives me that c is equal to 21 halves. Okay, so now I can say, well, if that's the case, then my function f of x is equal to 1/2 x squared minus 5x plus 21 halves. So I went from having a general, right, that we're used to doing in the previous examples, where we just slap that constant c out there because we don't know what it is, to now we have a specific solution, because we were told that when this function is evaluated at 1, that the answer is 6. Okay, so do you guys have any questions on that? All right, so that is all of section 1. I think what we're going to do now is go ahead and we'll move into section 2, and we'll, work on section 2 for a little bit, maybe halfway through it, and then we'll take a small break, and then continue after a break, just to make sure you guys kind of get a little bit of a breather from that. Okay. So what we have here, is now we're going to look at, integral calculus studies the accumulation of units as the input variable increases, okay? And the best way to express this is through an example, okay? So what I have here for you is imagine that a vehicle travels 50 miles an hour for 2 hours. How far has that vehicle traveled after those 2 hours? Most of us, because we drive cars probably every day, we could do this in our heads off the top of our minds relatively quickly, right? We'd be like, well, if I drove 50 miles an hour and I drove for 2 hours, then I went 100 miles, right? Does anybody disagree with that? Okay. Well, we can treat the vehicle's velocity as a function. Okay. If we treat the vehicle's velocity as a function and we say that v of x is equal to 50, right? Then when we graph this function, we can sketch a vertical line at x equal to 2, right? So x equal to 2 because we've gone 2 hours. And our function for our velocity is v of x equals 50, okay? And that's because I've held constant the whole time. From 0 to 2 hours, I kept this speed of 50 miles per hour, okay? So I've obtained this rectangle here now. Okay, this rectangle measures 2 units horizontally by 50 units vertically. So its area is the distance that the vehicle has traveled. Okay, so the area is going to be 2 hours times 50 miles per 1 hour. The hours cancel and we end up with 100 miles. Okay, so this area here is the area that the vehicle has traveled. It is 2 times 50, which is 100 is the area, right? So you've traveled 100 miles. Okay, question. So that's a very basic example. When we come over here, if you look at this is on page 398 of your textbook. So in the previous example, the area was pretty simple to calculate, right? This one in this picture isn't always the case. In this situation, it's necessary to use what's called the Riemann summation, which is the process where we can use rectangles to approximate the area under the graph of a continuous function, okay? So for example, this graph here, if we break this bin into, we're going to divide our intervals. So we have this interval from A to B, right? So our X goes somewhere from A to B. We're going to divide that into 4 subintervals, okay? So subintervals with the width of our change in X, which is B minus A over 4, because we want these to be 4 equal parts, okay? And then the height of our rectangles are going to be either, it's going to be f of x1, f of x2, f of x3, f of x4, okay? Those are the heights of our triangle. So the area under the region, or the area of that region that's underneath the curve is approximately the sum of those areas of the 4 rectangles, okay? So that would be something like my function evaluated at x1 times my change in x plus the function of my evaluated at my second x and what is my change in x plus the function evaluated at x3 change of x plus the function of x4 evaluated at or times the change of x, okay? So we can denote the sum with summation or sigma notation, which uses the Greek capital letter for sigma, okay? So that is this capital E looking, that's sigma. And so we could write this equation up here, this one that we've just written out, we can write that in summation notation. We can say that that is my function as for x, and we're going to put this little I here, and then our change in x. And then we're going to say I goes from 1 to 4, okay? So that is sigma notation. And so essentially that is saying that we are going to, it reads the sum of the product, f of xi, change of x, from I equal 1 to I equal 4, okay? To recover the original expression, we then substitute the numbers 1 through 4 in successively for I in this formula here. And we write a plus sign between each of the results, okay? And so essentially you get back up to what we have on the previous line, okay? Does anybody have any questions about how we get from this line to this or this up to the previous line? How to make that translation?
My question is, Professor, is like for the test, right? Which one would be the answer?
Yes. So in this case, we're just showing a general form right now. So we haven't actually even worked a problem. On the exam, it'll definitely be clear what is being asked of you. And we'll see some examples here in a little bit on how we would utilize this, right? So essentially, you might see this given to you on the exam. And in order to get a solution, you have to do this. Does that make sense?
Yeah, that makes more sense.
Yeah.
Okay.
So essentially what we could do is, let me move the things around just a minute. So this is really, oops. That. They're equivalent. So this is just saying what I'm doing here is I take this whole equation and I start with this. So everywhere I see this I replace it. So I'm f x1 delta x. Now I increment that, right? So I went, okay, my I was 1. Now I increment it. Now I'm at 2. So I do plus f of x2 delta x. Now I increment it. I'm at 3 plus f of x3 delta x. I increment it. Now I'm at 4. F of x to the 4th delta x. Now I increment, I'm like 5. I'm like, oh, wait, but I was supposed to stop at 4, so I'm done. Does that make sense?
Yes.
All right, so if I, well, let me give one more example over here of sigma notation. So if I had something that was 2 plus 4 plus 6 plus 8 plus 10, right? So note that we're adding consecutive values of 2, right? So this we could write in sigma notation as I equals 1, and we're going up 1, 2, 3, 4, 5 times. So we have 5 things. And so that's 2 times I, right? So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. Okay, so if you were to check that work, that's what that would be. 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. Okay, and that is 2 plus 4 plus 6 plus 8 plus 10. Okay, questions? All right, so if we're only looking at one specific area, here is the Riemann sum, okay? And essentially that's saying if we want to find the exact area under a curve, then we could do integration from A to B. That is the interval on which we want to look at the area under the curve. And we can evaluate to get a definite integral. Okay. So if we look at an example, in this case, we have the integral of 6 dx as it goes from 0 to 5. Okay. So the region of the rectangle, area equals base times height. So this is, if we look at this, we're going from 0 to 5. So we could kind of draw that line up here, kind of like the car one. And we're holding out constant for this example anyways at 6. So this whole space under here is our area. And that is the area is my base is 5, right? This is my base. And this is my height, right? So 5 times 6 equals 30. So the definite integral as the integral goes from 0 to 5 of 6 dx is equal to 30. Okay, question. So what if it's not something that's as simple as this constant that we had here, right? So then what do we do? So in this case, it's a piece part, right? So the region is a trapezoid, and we have to decompose the trapezoid into a triangle and a rectangle to help get that, right? So basically, if you recall, we could say this is our integral as we have 2x dx plus the integral from 0 to 5 of 5 dx, okay? So this gives me, we can say, all right, so if we had the constant 5, right? So we have this constant 5 that holds steady. We're going from 0 to 5, so let me get a different color first. So we're going to be limited in this space here, right? Like we can't go beyond 5 because we're only going from 0 to 5. But for the first piece, we have this area, which is covered by the second portion, okay? It's always easier to put the constant on the bottom so that it's a little easier to do. So this space here is 5. This space here is 5, right? So if I am, this is my area 1. And let's just do some highlighting. So this is my area 1 right here, okay? And that area is based off of, it's a rectangle, so that is just area 1 equals base times height. My base is 5, my height is 5, so the area here is 25 units, okay? For the next piece, we're just saying, how do I graph this 2x, right? So essentially, I am saying if I'm starting here instead of at 0, I'm just going to rise 2, run 1, rise 2, run 1, keep doing this, right? And I end up until I run into, something like that. So essentially, it'll be here at the 15, okay? And so you can see that this height is 10. This space here is still 5, right? So my area 2 is going to be my base times my height divided by 2, because that is what the area of a triangle is, right? So area 2 is base times height divided by 2, because we're only doing half of that rectangle, we're not doing this portion of it, okay? So base times height, my base is still 5, my height is 10 divided by 2, so that's 50 divided by 2, and so it's still 25. So when I want to know what the definite integral is, okay, so my definite integral then is the derivative from 0 to 5 of this 2x plus 5 dx is equal to 50 because it's 25 plus 25, which equals 50. Okay, question. Okay, so for this one, we have an application problem. So it says Paul rides a bicycle at a constant speed. His velocity is given by V of t equals 12, where t is in hours and V of t is in miles per hour. Okay. So part A wants to know how far did he ride in the first 2 hours. Okay. And so part A is we're just doing V of 2 hours. So that is 12 times 2 hours equals 24. So Paul has rode 24 miles in the first 2 hours. Okay. So part B wants between 2 hours and 4 hours. Okay. So that would be the amount of time. Let me just, so we have more room. So 4 hours minus how far he drove in 2 hours. So if you think about that, you're looking at, if this is 2 hours, this is 4 hours. We know here he drove 24 miles, right? And we want to know how much did he drive in the next 2 hours, that middle portion, right? So we would have to say, okay, V of t, this would then mean this would be 12 times 4 minus 12 times 2. So that's going to give me 48 minus 24. So that is 24 miles again. Okay, so he's driven or ridden his bike 24 miles again. So in that second half, between the second hour and the fourth hour, he rode another 24 miles. Okay. Finally, what is the cumulative distance he has ridden after 4 hours? So in that case, if we want to know what the cumulative distance is, that's just 24 plus 24 is equal to 48. And that would be our cumulative distance. The 24 plus 24 equals 48 miles. Okay. So he rode 48 miles in that 4-hour window. Okay, question. All right, so actually I only have one more example, so we'll go ahead and cover this one, then we'll take our break and come back and do section 3. So for this one, page 20, chapter 20, problem 20 in your textbook. So we're given a function. Our function is x squared plus 1, and we're given an interval, or our a is 0 and our b is 5, because that's the interval we're given. Notice there are brackets on the 0 and the 5. That means that 0 and 5 are part of our interval. Okay. So let's focus first on this first picture here. First of all, we know that our function is x squared plus 1, but we have to determine what our delta is, right? So our delta x is equal to b minus a divided by b, right? Or not by b, but by however many elements we have here. So in this case, we're dividing it by 5, because we have 1, 2, 3, 4, 5 equal parts. Okay. So this is 5 minus 0 over 5. So my delta x is equal to 1. So our a is approximately the summation I equal 1 to 5 of f of x I delta x. Okay. So what does that look like when we write it out? Okay. So in this case, we start out as 0 as our first value. So we have evaluate f evaluated at 0 times our delta x, which is 1, plus f evaluated at 1 times delta x, plus f evaluated at 2 times delta x, plus f evaluated at 3 times delta x, okay? And plus f of 4 times delta x, okay? So that gets me all 4 of my, so it goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, okay? When we evaluate this, my function, well, remember my function is x squared plus 1. So my function evaluated at 0, so that's x squared plus 1. So that's really 0 squared plus 1 times 1. I don't need to put that times 1 out there anymore. Plus, we have 1 squared plus 1, plus 2 squared plus 1, plus 3 squared plus 1, plus 4 squared plus 1. Okay. And remember, we're still multiplying it by that delta x. It just happens to be all ones out there. Okay. So 0 squared plus 1 is 1 times 1 is 1. Plus 1 is 2 times 1 is 2. 2 squared is 4 plus 1 is 5. 3 squared is 9 plus 1 is 10. And 8 squared is 16 plus 1, so that would be 17. So when I add all of those together, I get a total of 35. So the area underneath this curve, all of those yellow boxes added together gives me a value of 35. What I want to point out here to you, all of this space is unaccounted for. Okay, so we're not completely perfect. We don't have all of that space covered, but it's better than if I had straight line estimated and overestimated, right? So which one, you could be overestimating, you could be underestimating, but this is just an estimate. But when you start seeing all that gap in space, then you have to think, well, maybe I should work, if I could, maybe instead of having 5 things, let's try having 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different boxes. And now you can see in this one that the amount of space that is left here is actually a little bit smaller than the space if we had just left it with only 5 bins, right? So there's still some missing information here if we looked at it in that sense, but there's less green than there is purple up there at the top if you added all that stuff together. But the other thing you could do is you could make those bins even smaller. What if I went to 20? What if I had 30? And the smaller I go, the more accurate I get about the amount of area underneath that curve. Okay. So when we do the math out on this one in the green, and we're not going to do all of the math out, but I'm going to show you. But so we end up here, our delta x here, again, b minus a, but now we're going to divide by 10 because we have 10 bins, and that equals 0.5. Okay, so a here is approximately the summation as I goes from 1 to 10 now of my function f of xi dx, or dx is just the change in x. Okay. So how do I do that one? Let me just make this a little bit over here, make it a little bit smaller. And so for this one, that is going to be f of 0 times 0.5 plus f of 1 times 0.5 plus dot, 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 all the way out to f of 9, not 9, sorry. It's 0 to 0.5. Let's put 0.5 because see, we're having 0, 0.5 because here's 1 and so on, right? So this is going to be 0.5. I'll put one more in here. So we know this is f of 1 times 0.5 plus dot, 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 all the way out to f of 4.5 times 0.5. Okay. So you do that for all of those. So for each of those, 0.5, 1, 1.52, 2.53, 3.54, 4.5. We do the math, right? So this is, again, the 0 squared plus 1 times 0.5 plus 0.5 squared plus 1 times 0.5. All that plus all that to 4.5 squared plus 1 times 0.5. Okay, so when you do that, you add all those up, you end up getting 40.625. And that is a much more accurate amount of space than if we just had 35, right? But both of these are more accurate than if we just did straight line method and drew a straight line and said, okay, the area underneath all of that curve is whatever. It is not as straightforward or as accurate as using the Riemann sum here, where we can get a more accurate depiction of the area underneath that curve. Okay? Questions? All right, so it is 8:06. So let's take a 10-minute break. We'll come back at let me pull up this one. We will come back at 8:17 p.m. Okay, so we'll return at 8:17 p.m. and we will do this last section, the area about area and definite integrals. All right, it is 8:15 or 8:17. So let's go ahead and continue on with the remainder of tonight's lesson. So we're going to move into section 4 or section 3. And so in this section, we're going to look at the area and definitive integrals, right? So at the end of this, we'll be able to find the area under a graph of a non-negative function over some given closed interval. We'll evaluate definite integrals, and then we will also solve some application problems with the definite integral. Okay. So first we have theorem 4, where it is saying if we let some non-negative continuous function from over the interval from 0 to b, we can evaluate that and determine what that area under the graph is. Okay, so to look at this in an example form, so basically think of this as this is really the fundamental theorem of calculus. Okay. You can read more about the fundamental theorem of calculus on page 405 in your textbook, but essentially it's saying if you want to find, the area under this non-negative continuous function over that interval from A to B, that we need to find an antiderivative, okay? And the simplest one, we need to find any antiderivative. Okay, because remember we've been doing the plus C out there. So the most simple one to find is if we let that constant C equal 0. And then we want to evaluate that function using B and A. So we would compute our function evaluated at B minus our function evaluated at A. And the result is the area underneath that. Okay. So how do we do this? So let's walk through an example here. We want to find the area under the graph y equals x squared plus 1 over that interval -1 to 2, where -1 and 2 are included because we have the brackets there, okay? So first, we want to find any antiderivative. Okay. So when we find any antiderivative, that is for our function of that capital F of x, right? So if we want to choose the simplest one, right? That is, so the antiderivative of x squared plus 1 is x cubed over 3 for the x squared plus x for that. And in the previous section, remember we would have that plus C out there. But we're going to let C equal 0, and thus we're going to just look at, we'll just cross that part off. Okay, that looks not like a let there. Okay, so now we'll say that our function is x cubed over 3 plus x. Okay, now the second thing we want to do is we want to substitute 2 and -1 and find the difference. Okay, so that is taking my function, evaluating it at 2, minusing my function at that -1. Okay, so this is going to give me 2 cubed over 3 plus 2 minus -1 cubed over 3 plus that -1. Okay, so this will simplify to 8/3 plus 2. Distribute that minus to both pieces. So this ends up being a plus 1/3 plus 1. because we have those negatives in there with that. When we simplify this equation, we get 6, right? So we have 8/3 plus 6/3 plus 1/3 plus 3/3. That's going to give me 18/3, which is 6, okay? So the area under this curve of y equals x squared plus 1, the area would be 6 units, okay? Question. Okay. So now let's look at our definite integral then, right? So really what we did this portion here, right? I didn't define it out to you as that's what a definite integral is, but that is what it was, right? So that fundamental theorem of calculus is really saying that I can evaluate any of these functions across that interval, and the answer is going to be my definite integral, okay? So we have a couple of examples here. And so this first one, if I wanted to take the, evaluate the integral x squared minus x dx from -1 to 4, the first thing I want to do is take the antiderivative. So we can do it in pieces, right? So the antiderivative of x squared is going to be x cubed over 3 minus the antiderivative of x. So that's just going to be x, and we have 1 plus 1, so that's squared over 1 plus 1, which is 2. And I want to evaluate this from -1 to 4. Okay. So when we put that symbol like that, that's saying I'm going to do this entire thing evaluated at 4 minus the entire thing evaluated at -1. Okay. So this would then become 4 cubed over 3 minus 4 squared over 2 minus -1 cubed over 3 minus -1 squared over 2. Okay. So this gives me 64 over 3 minus 16 over 2. This would then be minus negative. So we have a negative and a -1. So that's positive 1/3 plus 1/2. Okay. And so when we simplify all of that, we get 85 over 6. So the area under this curve right here is 85 over 6 units. Okay. Questions? All right. So let's look then at another example. So we want to evaluate the integral. Now it's a little crazier, right? We have this x minus 1 over x dx, and we want to evaluate that from 1 to 5. So how do we do that, right? So this is going to be the same as the integral from 1 to 5 of x over x minus 1 over x, right? That's really what that's saying. I'm just, instead of having a common denominator, now I'm breaking that out. Well, x over x is really what? It's just 1. So we have that constant, so that's okay. So when I break this out, then my antiderivative is going to be x minus the ln of x. Because I'm going from 1 to 5, I don't have to put the brackets around that, because I know my a and all the way through my b is greater than 0, so I don't have to put the absolute value sign on that ln of x. Okay. So this gives me 5 minus ln of 5 minus 1 minus ln of 1. Okay, so all I'm doing is substituting my top value, which is 5, in for all the x's, minus the bottom value in for all the x's. Okay, and so this gives me, well, the ln of 1 is really 0. Okay, so this gives me 5 minus ln of 5 minus ln of 5 minus 1. So that equals 4 minus the ln of 5, and that's approximately 2.39. So the area under the curve for that graph from x equal 1 through 5 is going to be approximately 2.5. Okay, questions? All right, so I mentioned in the last while ago when I was talking about the fundamental theorem of calculus. Well, here's the fundamental theorem of integral calculus, right? So if we have a continuous function f and it has an antiderivative, that capital F over our interval from a to b, where that a and b are both inclusive, then we can take the limit as n approaches infinity of that summation, and it is equal to the integral from a to b of that function, which is the same as the overarching function evaluated at b minus that overarching function evaluated at a. Okay, so how do we go about solving an example or a specific of that, right? And so this example that we have here, is if you're considering we have this function or this integral from -1 to 2 of negative x cubed plus 3x minus 1 dx. And we want to predict the sign of the integral by looking at the graph, then we can evaluate it afterwards and see what that value should be, right? So when we look at this picture of this graph, right, we can see, well, it appears that there is considerably more area below the graph, right? So we're looking on this interval from -1 to 2. And so we can look at this and determine, if you look at this space here that's colored in, all of this space along with this space looks to be a considerably larger area than if I looked at just this space, right? So essentially, in estimation wise, if I look at this, I should expect that the sign of my integral, when I do all of this work, I would expect that the sign of my integral to be negative because I have more of the graph below the x or the y-axis below the x-axis than I have above the x-axis. Okay. So that's just one observation, that when we get to the very end, I would like to just say, hey, did our integral end up being positive or was it negative? And by looking at this picture, I would hypothesize that it's going to be negative. Okay, question. Okay, so let's evaluate this. Okay. So if I'm evaluating this, negative x cubed, so that's negative x, 3 plus 1 is 4. So 3 plus 1 is 4. Okay. Plus 3x, 1 plus 1 is 2. 1 plus 1 is 2. Minus x, because it's just 0 plus 1, so x over 1. So we don't really need to have that 1 on the denominator. We're going to evaluate this from -1 to 2. Okay, any questions so far? Okay, so we're going to evaluate this. So we go from the top one. So we have negative 2 to the 4th over 4 plus 3 times 2 squared over 2 minus 2. Okay, and that's the first half, and we want to minus that from the second one, which is negative 1 to the 4th over 4. Let me shift this over just a little bit. Plus 3 times negative 1 squared over 2 minus the negative 1. Okay, so we simplify this, negative 2 or positive 2 times 2 times 2 times 2 divided by 4. That's going to give me 4. It's going to give me negative 4. Then we have 3 times 4 divided by 2. That's 6 minus 2. And then we have minus a negative 1/4. So that becomes plus 1/4 minus 3/2 minus 1. Okay. And so common denominator is a 4. So when we add all of this up together, we get negative 9 over 4. And you can see here, as I pointed out from our visual estimation, our solution here, or the integral, is going to be negative 9/4 if we take, because essentially if we're taking everything from below the graph and everything from above the graph, you put it together, you're still in the negative, because that orangish burnt color is larger than the gray shaded area. Okay, question. All right, so that is all of the material that I have for you all this evening. If you have questions, happy to stick around to answer any of those for you. Otherwise, I hope you guys all have a wonderful Thanksgiving break. Hopefully you're able to kind of recharge a little bit from the break, and then we can come back, have just a couple of weeks left in the semester, and you can finish out strong for that. Okay, so if you guys don't have any questions, you're free to go. Otherwise, if you do, feel free to unmute yourself and chime in.
Good night, Professor. Happy Thanksgiving.
All right, thank you. Have a good night.